So really the last frontier, if you will, in this unit is to look at assigning stabilities to di and tri-substituted cyclohexanes. There are many different permutations of this problem. Let's go ahead and look at the first problem on slide 43, where we have trans 2-methyl 1-chloro cyclohexane, and we want the most stable configuration of this molecule. So what we want to do I'll first draw this like it's planar. I think we all realize by this point that it's not planar. The first step is going to be to draw this in the chair conformation. And with a quick analysis, I usually, pick one to be axial, pick one to be equatorial. Now, I want to emphasize my equator rule. And my equator rule kind of goes as follows. I draw an equator along the plane that contains the 4 carbons that are in the same plane. And below this plane I call south, and above this plane I call north. In other words, I treat this like an equator. And so trans means one goes north and one goes south. Cis means they both go north and they both go south. Also, in order to reaffirm our axial and equatorial positions, I'm going to go ahead and draw those into place. Now we only need 2 of these. And I'm going to go ahead and draw the equatorials into place as well. Remember, this one's a little on these 2 are a little on the tricky side. So I'm going to choose to put the methyl group axial. This is going north of the equator. And so chlorine would need to be going south of the equator on the next carbon. And so that means that they need to be trans-diaxial. Remember, axial is a more sterically hindered position than an equatorial because of the fact, and I guess now we can clean this up just a little bit because everything else is a hydrogen. What I want to draw are the diaxial hydrogens. So I'm going to get rid of the equatorial positions that kind of cloud up this picture just a bit. So here's an axial hydrogen, and here's an axial hydrogen. Here's an axial hydrogen, and here's an axial hydrogen. The whole point is that you are going to have steric clashes with the methyl group and these hydrogens above the plane, and with this chlorine atom and these hydrogens below the plane. Remember, at room temperature, we can undergo a ring flip. And this is going to be equilibrium that favors products, because when I do the ring flip, what was the head is now the foot. So if we label these carbons 1, 2, 3, and 6. I'm choosing this numbering system just because that's what we've done in the past. Carbon 1 is now at the bottom. Carbon 2 is right here, and then 3, and then 4, and then 5, and then 6. Real important that you understand you can't just redraw this chair and put the axials to equatorial and the equatorial to axial. When you do the ring flip, however, on carbon 3, the methyl that was axial is now equatorial. And the chlorine on 4 that was axial is now equatorial. This is much more stable energetically. And so this would be the predominant conformation. Now let's play the role of devil's advocate just a bit here. And let's look at just a slightly different structure. Let's look at cis 2-methyl 1-chloro cyclohexane. Because when you can put both substituents in the equatorial position, there's really no detailed analysis that needs to be made. But when one conformation has one in axial and one in equatorial, and by corollary, they'll flip, you'll still have one axial and one equatorial. Then you need to make some decisions about the bulkiness of your substituent. So we're going to start off the same way as we did before. And I am going to place, again, I want to emphasize the plane. Remember, our plane is right here. This is just to remind you about this equator rule. And so, of course, north of the equator, south of the equator. This is something that I came up with when I was studying chemistry as an undergraduate. It served me well. I never missed a problem with it. I think it'll serve you all well in addition. And so it's pretty infallible. And if you just take the time to do this, slow down just a little bit, you can make a really good detailed analysis of the energetics of these two conformers that we see. And so I'll put the chlorine axial. Again, I make an initial choice. I put it axial. The methyl group, now it needs to be cis. Therefore, this methyl group will have to be equatorial. So that if I were to continue my line, I am going north of the border. And of course with chlorine, I'm also going north of the border. I'm just going to shade these in. And I'm going to purposely make the methyl larger because a methyl group does take up more three-dimensional volume. When I undergo the ring flip, let's take a look at the conformation now. So my methyl group will now be axial, whereas my chlorine atom will now be equatorial. And if I begin to give this volume again, I'm trying to make this look obvious, but the fundamental question remains, do I want the largest atom or group of atoms in the axial position or in the equatorial position? The obvious answer is I want it in the equatorial position because it will minimize these 1,3 diaxial flagpole interactions. And so these are going to be different in energy, but by a smaller degree. So I'm going to call this the cis. Then the delta E of the trans, because in the trans you got one clear winner. The diequatorial is more stable than the diaxial. Let's take a closer look at some molecular models, because I really want you to be convinced that this is a true phenomenon. And so here we go. So these are from one of my old professors at Vanderbilt. Pretty good notes, actually. If you look to the left, you've got methyl cyclohexane, where the methyl is axial, and it is positioned to interact with these two red hydrogens. It's more apparent when you take into account the van der Waals radii. These will interact with one another. On the other hand, when the methyl group is in the equatorial position, it will not interact with the hydrogens rendered in blue as it rotates. So there is a definite preference for the methyl group, for the biggest and bulkiest group of atoms to be in the equatorial position than in the axial position. And that is really the bottom line when doing this kind of conformational analysis. If we look at slide 43, we see we have two conformations.
By taking our work home with us, and today we're beta testing.
You know, one of the problems with being as awesome as I am is you try to multitask, and so that was the game cast of me watching the Grizzlies game. I'm pretty upset with them right now because they're only up 4 at the Washington Wizards, which is absolutely freaking ridiculous. Don't even get me started on this. So let's go back and look at the fact, this is what we drew structures for. The molecule on the right is definitely favored relative to the molecule on the left. You could do the same kind of analysis for 1,3s where the substituents are different. However, same thing is going to apply. We want the ethyl group to be in the equatorial position. So even though methyl is big and bulky, when we start looking at the energetics, we'll find that there's a greater energetic cost for an ethyl group because it takes up more volume in three-dimensional space. So the molecule to the right is the lower energy conformation relative to the molecule to the left. And you'll see the same thing on this particular example. You want the ethyl group to be in the equatorial position, and with 1,3 trans, one has to be axial, one has to be equatorial. And I think that's where we need to go next. Let's take a look at 3 different scenarios where we have, just to be different, I'm going to go with the checkered background because I know you all hate it. I have all the power. Let's look at 1, 2, cis. And I think we can really take some lessons from what we've previously learned, because 1, 2 cis is going to have one of these methyl groups axial and one of these methyl groups will be equatorial in each conformation. And again, let's remind ourselves of the plane. In this case, we're both going north of the equator. CH3, and CH3. When I do the ring flip, one is axial and one is equatorial. Absolutely equal in energy. Remember, the word we use for this in chemistry is degenerate. Equal in energy. So delta E between these two is equal to 0. Now let's consider 1, 2 trans, and we've already seen the answer for this one as well. I just realized I drew 1, 2 trans for this guy. I meant to do 1, 2 cis. Here's 1, 2 trans. Again, chair conformation. I will have both axial, which is not nearly as good as having both equatorial. So in the 1, 2 disub, trans will always be lower in energy than cis. There's a difference between the energy of these two, whereas there's no difference in the energy between these two. 2 equatorials is superior to 1 equatorial when you're comparing very similar molecules. So when there's 1, 2 disubstitution, the advantage goes to trans. And now let's look at cis. Again, it's going to be very structurally similar. So when I draw my chair conformation, when you guys kind of get the hang of doing these chair conformations, this is going to be very simple to analyze a lot of these very, very quickly. So we're going to have a methyl group that goes north. And we're going to have another one that goes north, and this has to be axial. Both of these are axial. Which is not nearly as good as when they are both equatorial. So the molecule conformation to the right is lower in energy than the conformation to the left. Let's now look at 1, 3 trans. If you've really been paying attention, you know the answer already before we even draw this. Again, let's make our equator, draw our plane. That's not a good color. So this can only be trans if this is equatorial. And when I do the ring flip, I'm going to have 1 axial and 1 equatorial as well. Those are equal or degenerate in energy. So there's no difference in energy. So when I have a 1,3 disub and the substituents are the same, the advantage goes to cis. One other type of disub we can have, and that's going to be 1,4 cis and trans. Do the 1,4 cis first. Again, always draw the chair conformation. One, two, three, four. Only way this can be cis if this is equatorial. So we already know from the chair flip, axial becomes equatorial, equatorial becomes axial. I'll still have one of each. So this becomes axial, while this becomes equatorial. This is going to be a little awkward to draw, but you're going to have a methyl group coming out this way as well. These are degenerate. Now let's look at 1,4 trans quickly. One, two, three, four. So when I do the chair flip, the diequatorial will definitely be favored. Equatorial and equatorial. So when it's 1,2 or 1,4, trans is favored over cis. When it's 1,3, cis is favored over trans. I'd like to stop this podcast at this point so it doesn't get too long. I do want to do one last one where I do some examples. Be prepared in class on Wednesday to work a lot of problems so that we feel good about this material, because we get one class shot at this. And also really be thinking if you guys are available this Saturday or Saturday the 22nd to meet in order for us to have one of our makeup classes.